All right. Well, it is Friday, week 9. I guess next week's week 10. And today we'll cover PCA. PCA is Principal Components Analysis. And so this falls under unsupervised learning. And here, we talked about clustering as unsupervised learning, and then kind of another aspect of unsupervised learning could be dimension reduction. And so, the big picture idea here is you start off with a data set, a whole bunch of variables, okay, and then a lot of these variables might be correlated with one another, okay. And what PCA will do is it will transform the data into uncorrelated variables. It'll find some kind of linear combination, so it's not going to be doing any kind of operations other than multiplying by a constant and adding or subtracting the variables. So it's not no like squaring or log or anything like that, just linear, some kind of linear combination. And so we create, we get these kind of, I guess, quote, recipes for new variables using linear combinations of the currently existing variables. And then once we have that, then those resulting variables will be uncorrelated. And then usually we do PCA because our hope is to achieve dimension reduction. And the idea is it's a lot easier for us to kind of think about just a few variables at a time rather than a whole bunch. And so can we kind of reduce the number of variables and still kind of capture or convey the kind of the original variation that exists in the data, okay? But kind of by definition, a reduction in variables is going to result in a loss of information. Okay, so if you used to have 30 variables and you go down to 3 variables, you're going to lose some information. But the idea is you want to kind of minimize the amount of information that you're losing. Okay, so here's just a simple example, maybe a silly example. Housing prices. And this could also apply to apartment rent costs and things like that. So I feel like in 101A, it's pretty popular to use like a housing data set or something. I don't know if you guys used some kind of housing data set in 101A maybe. But you have a bunch of these variables, and a lot of them are going to be correlated. So you have things like livable square footage and total square footage, which might include like a basement, and the number of bedrooms, number of bathrooms, the lot size, if there's a pool, the roof style, what kind of home heating there is there a garage, maybe a rating for the kitchen, a rating for the floor, a rating for the roof, information about the location and zip code, or maybe information about the surrounding areas, like how close are you to a park, or what's the local school, or something like that. And so you might have a whole bunch of these variables. In some cases, you end up having something like 70 variables or something like that. And I would argue that you can kind of boil down these, kind of group them all together, and you might just come up with kind of 3 important pieces of information. And one would be like the size, as measured by the square footage, number of bedrooms, number of bathrooms, or something. Usually those all go together. Another could be the amenities or the quality. Is there a pool? Is there, how nice is the place, basically? Does it look new or does it look old? Things like that. And then one would be, the last one would be kind of the location and the desirability of that neighborhood, or something like that. And another way you can think of this is like, um, say you go, like if you go on Airbnb or something and you're looking up a place and you type in a search and you get all of these results, right? Each of the places has tons of information that you can get when you click each of the things. But on the results page, what are the pieces of information that they should display on the results page? Okay, and it will probably be like, because you can only fit a few variables. So what are like kind of the most important variables? And one will probably be like something related to the size, and then another might be, some like the neighborhood location or something. Okay, maybe distance from the landmark that you selected, or whatever it might be. And the idea again here is it's harder to think about 20, 30 variables at a time. It's a lot easier to reduce them down to just kind of maybe 2 or 3 things to think about. Other examples of dimension reduction that make it easier to kind of think about. One is your GPA. Okay, this is it basically takes someone's entire academic career, academic performance at an educational institution, boils it down to a single number. Okay, it is by definition very reductive, but it's useful in that it can be used to make a quick comparison between different students. Okay, so if you have one student with a 3.9 and another student with a 2.9, there's a kind of a big difference. And again, it doesn't summarize everything. There's there's a lot of information that is lost. But as far as like a quick comparison between individuals, it can be useful. Again, if you were on some kind of admissions panel or something and you're judging students, there's a whole bunch of different things, aspects to take into account about the student, right? And then you have these essays and all of these things that you have to kind of dedicate. And if you have hundreds of these applicants and you have to kind of think of all of these things, it's really hard. But if you got a kind of a GPA and you can kind of just sort them in the beginning and just say, all right, we'll just draw a cutoff line here and then reduce your applicant pool. In that sense, it can be useful, but again, very reductive, right? Similar things with like SAT or GRE scores. It takes something very complicated and very kind of multifaceted as far as like a rating of, I don't know what it attempts to do, but maybe it tries to measure something like, quote, intelligence or academic achievement or something like that. And it basically reduces it down to maybe like a mathematical or quantitative score and a language reading, writing score, maybe like 2 or 3 scores in total that you have. Okay. Credit score is this concept of financial trustworthiness. Like if somebody lends you money, how likely are you to pay them back, or perhaps possibly not pay them back? And so it takes into a bunch of things and it boils it down to a single number, right? A credit score. And this number is going to determine whether or not you can get a loan for a new car or open a new credit card or something like that. Usually banks that when it comes to lending somebody money make their decisions based on like credit score and annual income. And those will be kind of like the two primary factors. And again, very kind of reductive. If you think about sports, here, how do you rank one player against another or something like that? And it's difficult because different players have different kind of abilities and things like that. And so for like football, NFL, if you wanted to compare one quarterback with another quarterback, how do you do that? And one quarterback might be more talented in a certain way, and others might be different. And so there's one number called the passer rating, and it's kind of this complicated formula, but it's supposed to kind of just boil down this quarterback's performance in a game, or even performance in the entire season, down to a single number. And you can say, okay, Tom Brady gets this score versus I don't know, someone else gets a different score, right? So things like that. Another idea is like in sports, you have events in the Olympics. You have like heptathlon or decathlon, where individually you have like in these individual events like running or hurdles or javelin and things like that. But then you also have these kind of combined things where they compete in multiple events, and so one person might have been really good at the running but not so good at the throwing, and another person did really well in the throwing but not as good as at the running. How do you rank them? Okay, you can only have one ranking of best to worst as far as like determining who gets the gold and silver and bronze and things like that. And so that's a dimension reduction problem. So anyway, these are just examples of when you might want to use dimension reduction, or I guess examples of dimension reduction that we might encounter. I guess another way to think about dimension reduction is you can think of objects that cast shadows. Okay, and so we basically, everything that we interact with, every physical object we interact with exists in 3 dimensions. Okay, but when you shine a light and that 3-dimensional object casts a shadow, the resulting shadow is 2-dimensional. Okay, and so that is an example of dimension reduction. You're going from a 3-dimensional object to a 2-dimensional shadow. Okay, and depending on how that shadow is projected, the resulting shadow might resemble the object or it might not. Okay, and so I'm going to kind of come up here and just show you, like, here is my hand in 3D, and then when you see the shadow on the board, it's very clearly a hand. Okay, if I turn it to something like this is not as easy. Like, you can probably tell it's a hand, but you don't know which way it's facing. Okay, you don't know if like the thumb is facing towards you or away from you or something like that. It's a little bit harder to distinguish things. I could take, say, okay, here's a pen. Okay, and if you see the shadow like this, you can tell it's a pen. If the thing was projected like this, I don't know, it could appear like it's a little ball or something, right? The shadow is, so depending on how the orientation of the object will determine basically like how much information you can get out of that reduced state. Okay, and so the goal when you do dimension reduction is you want to find a projection, find a, quote, rotation of your data that minimizes how much information is lost, or basically maximizes the amount of information that's retained. Again, by definition, when you reduce the number of variables you have, when you do dimension reduction, you are losing some information. But the hope is you're going to lose the least important information. Okay, that you're going to pick a shadow so that when you see the hand, it looks like a hand rather than something that's harder to kind of tell what it is. And so, here, let me give you your first view quiz answer, which will be the letter E. E as in elephant. Okay. All right. So yeah, when we say we want to kind of find a lower dimensional projection that resembles the original data, one way we can think about it is we can say we want the resulting projection. So when you go from 3D down to 2D, we want that resulting projection to capture as much of the variance that exists in the original higher dimensional data. Okay, so we want the resulting data to have kind of the most amount of variance possible. Okay, so again, when we reduce the dimensionality of the data, we won't be able to capture all of the variance, but we still want to find one that has a high amount of variance. Okay, and so we're going to search for basically a lower dimensional projection that maximizes the variance in the resulting projected space. Okay, so here we'll start to see a little bit of math. So the original data exists in m dimensions. Okay, so every observation you have is a vector of length m. Okay, and we want to find a lower dimensional projection with d dimensions, where d is a number that's less than m. Okay, and so after you project your original data, which we'll call y, so each observation in y is a vector of length m. When we project that observation down to fewer dimensions, we're going to get x. Okay, so x is our reduced data, and each observation in x is a vector of length d. Okay, so you might have 100 observations in y, and maybe in 3 dimensions. So in that case, y is going to be 100 by 3. And then you want to reduce it down to 2 dimensions. So then your result will be x is a matrix with 100 rows. So you keep the same number of observations, but now you only have 2 columns. Okay, so it's going to be 100 by 2. And so how do you do that? Well, x is going to be found by taking y and multiplying it by some matrix W. Okay, W is basically going to be a 3 by 2 matrix so that whenever you multiply y and W, you do W transpose y, the result is you're going to get basically linear combinations of the 3 variables in y, and you'll get basically, you have 2 recipes for that, one for each column in x. Okay, so yeah, so if you have 3 dimensions and you want to go down to 2 dimensions, you're going to basically get 2 recipes, one for x1, and it's going to kind of show you like how do you combine the 3 variables in y. So you're going to say like take the first column and then take the second column, multiply it by -2, and then take the third column and multiply it by 0.5 and then add them together or something like that. Okay, it's basically like a recipe of the variables that currently exist in y, and how do you combine that? Okay, so that will be like recipe for x1. And then the recipe for x2 might be take the first column, multiply it by 0.1, take the second column, multiply it by 5, and take the third column and multiply it by -3, and then combine those together, and you'll get the recipe for x2. So basically you take your y, multiply it by w1, and you'll get your component for x1. You'll take that same observation y multiplied by w2, and you'll get your component for x2. And so so the goal is, okay, well, how do we figure out that recipe in W? Okay, how do we figure out how much of each of these variables in y do I want, and how do I combine them? How do I figure out this recipe? And so if let's just think about that first vector. We want the weights in that first vector of w so that the resulting projected values, which will be our x1 values, the variance in x1 will be as high as possible because we want to kind of maximize the amount of variance captured here. Okay, and then we'll say when we look for w2, we have this other goal that all of the variables are uncorrelated with each other. So w2 is going to have to be orthogonal to w1. Okay, so we want to maximize the variance in x2, but we have this criteria that it is orthogonal. So w1 transpose w2 is going to be 0, and so on and so forth. W3, if we were to search for that, will be orthogonal and whatnot. Okay, so all of these w variables vectors are orthogonal. Sorry, there's a typo here. Wi transpose, it should say Wi transpose Wj, not the same subscript. This one should be a j. Is going to be 0 for all I not equal to j. Okay, and then if you leave these unbound, you could just and you say we want the values in x to have maximum variance, and x is just found by doing w times y. You could just pick really big w's, and so we'll put in a restriction that basically the length of each vector is going to be 1. So w transpose w is equal to 1. Otherwise, you can just say all of my components in w are infinity, and that will maximize your variance. So the length of w itself has to be 1, and we want to find kind of what direction should w point in. So you can think of w as basically unit vector, but it's going to be some combination. So what direction does w point in? Okay, so so we'll work through deriving what w1 is, so that the resulting data, when you do x times w, I'm sorry, y times w, and you get x, that the variance in x is maximized. So to kind of make our work easier, we will center our original data in y. So we have our original values in y, and basically we'll subtract y bar from each column, so that when you take the mean of your centered data, you're going to get the zero vector, a vector of zeros that for m-dimensional y. Okay, and then we'll just kind of look at the first vector. All right, so for each observation in y, we're going to multiply one of our weight vectors w times y, and that will reduce it down to a single scalar value. Okay, so normally you have multiple of these recipes, one for each component in x, but here we're just going to look at the first component in x, and so we'll just have one recipe. Okay, so if y is 3-dimensional, w will be a vector of length 3, which basically tells us how to mix the different components of y together into one component. So w is a vector of length m. Each observation in y is a vector of length m as well. And when you do w transpose y, you'll get a single scalar value. And what is the variance of this of x? Okay, we'll just use the definition of the variance here, using 1 over n rather than 1 over n minus 1. But we'll treat it kind of, I guess, as our population. So we'll do x minus x bar squared summed up divided by n. So that's the variance of x. Okay, and we want this to be maximized. So one thing to note is that because we centered y and the mean of y is 0, then the mean of x bar, or I'm sorry, the mean of x bar is also going to be 0, okay? Because, so here, we say, x bar is equal to basically the sum of the x divided by n. Remember, x is a scalar value here, and x is defined by doing w transpose y. Because w is a constant, or not a constant, but is not affected by our subscripts here, it's going to be the same. We can pull that out, and now we have basically the sum of y here, and we said this thing is basically the a vector of zeros. So basically you have w transpose times a vector of zeros, which is just going to result in 0. So x bar is 0. Okay, and then so now our variance, what is the variance of x? Well, we can simplify this, and we can say, okay, well, the variance of x is basically going to just be like x transpose x, but I mean, yeah, so here I can subtract off x bar, but we know x bar is 0 for everything, okay? So I got 1 over n, and then the sum of basically our x's squared. If each x is w transpose y, then w transpose y, that quantity squared, can be written as w transpose y, y transpose w. Okay? And then again, the w's are not affected by the subscripts, so we can pull them out outside of the summation. Okay? And so now we just have to take each y sub n, we'll do yn transpose, okay? Whatever y is, if it's a vector of length m, the result there is going to be an m by m matrix, m by m square matrix. But we're going to multiply it by w transpose and w after, and so the result of all of this is going to be a single scalar value for our variance. Okay, and so this is the thing that we want to maximize. Okay, so we want to maximize, we want to figure out the w, what w we should use so that the resulting variance should be maximized. Okay, so here I'm going to just replace this part here, the m by m matrix of yn transpose. We're just going to call that C. C is the covariance matrix. Okay, so the definition of the covariance matrix is y minus y bar times yn minus y bar transpose. But here, because y bar is 0, our covariance matrix reduces to this, and that's exactly what we have here. So we have the covariance matrix right here. So I got w transpose covariance matrix w. This is the quantity that I want to maximize. How do I find the w's to maximize this? Okay, we can do a Lagrange multiplier, right? So, so how do you maximize something when you have a constraint? So we have this constraint that w, the length of w, or w transpose w, is equal to 1. Because otherwise, if I just said maximize this thing, I could just pick my w's to be infinity, but that's not what we want. We want to figure out the w's with a length of 1 so that w transpose cw is maximized. Okay, so with the Lagrange multiplier, we'll subtract off lambda times basically w transpose w minus 1. Okay, so I don't know, do we remember Lagrange multipliers a little bit? These things, so we have this is basically what I have, and then so this is, we're going to try to maximize this, and we put in our constraint by throwing it in here, okay? And then to now to maximize this, what would we do? We'll take the derivative of this with respect to w, set it equal to 0, and solve. Okay, so when I do that, the derivative, or I guess gradient here, with respect to w, w transpose cw results in 2cw, okay? And then here I got negative lambda w transpose w, that's going to result in negative 2 lambda w, and then the 1 zeroes out. Okay, so this is our gradient. We set that equal to 0, and now we want to solve for w. Okay, so just kind of rearranging a couple terms, I have C, matrix C times w is equal to lambda. Lambda here is a scalar value times w. Does this form look familiar to anybody? From linear algebra? So here, what if I call this matrix? Matrix times vector is equal to scalar times vector. Yes, maybe? That sounds familiar, maybe? Okay. So that means W is an eigenvector of the matrix C, okay? And then lambda would be an eigenvalue, right? So when you say, a matrix times a vector is equal to a scalar times a vector, then that means that vector is an eigenvector of that matrix. Okay, so an eigenvector. The idea here is, basically all square matrices represent some kind of rotation or scaling of your, I guess, your coordinate plane. Okay, and usually when you kind of either rotate or scale your coordinate plane, most of the points on your coordinate plane end up somewhere else. Like if you have a vector on that coordinate plane, usually it ends up pointing somewhere else, okay? But there's a handful of vectors, okay, and these are the eigenvectors, that even after you multiply the kind of your coordinate plane with this matrix, those eigenvectors still point in the exact same direction that they used to, okay? And again, if this is, look up 3 blue, 1 brown, eigenvectors and eigenvalues. This is a great lesson, okay? So we have what, AV equals lambda V. This is, matrix times vector is equal to scalar times vector. Watch this video for just a quick refresher on that, okay? All right, so W is going to be a solution, or W is an eigenvector of your covariance matrix C. Lambda is the eigenvalue. And so kind of the eigenvector pair with the highest eigenvalue will be the projection with the highest variance. And then basically the next eigenvector is orthogonal to your first eigenvector, and that will kind of correspond to the next thing. Okay, so just to kind of illustrate this, we're gonna, or just to summarize all of this, to find your principal components analysis to go from M dimensions down to D dimensions, we center the data, so all the columns have mean 0, okay? And then we'll find the covariance matrix C, and then we'll find the eigenvector, eigenvalue pairs of that covariance matrix, and then we'll select a subset of those eigenvectors, and then we can compute our values x by doing y times w. All right, let me kind of just illustrate some of this. Do a quick example. Okay, so let me library MVT norm. Oops. And let's create a matrix Y, RMV norm. I want 100. Mean will be 0, 0. And then sigma will be, let's create correlated variables. So I'm going to make a matrix of, we'll do 1, 0.9, 0.9, 1, and row equals 2. So let me plot y. Okay, so here is a current plot of y. Let me let me find column means of y. Something close to 1, and let me just center my y. So I'm going to call y centered. And yeah, it's going to be basically transpose y. I'll transpose this back. Okay, so now if I do column means of y centered, I should get, yeah, 0. Okay. Okay, so we have that. My covariance. So if I ask for the variance matrix of y, covariance matrix of y, this is my covariance matrix, and I'll call this capital C. And all right, so now I can call, what are the eigenvalues and eigenvectors of C? So this will be, we'll call this EV will be this. Okay, and then so my first eigenvector is going to be 0.69, 0.72. So so I'll call this eigenvector 1, and we'll basically take my vectors, and I'll take the first column here. Okay, EV1. And so now what I'm going to do is I will take my y-centered values, and I'm going to multiply it by EV1. And so this is the result of my data. Okay. Here, let me just show you if a rotation of this is, I can just take the vectors. All right, so I'll call this rotated y. Is if I just take my centered values and I just multiply it by both eigenvectors, okay? And so if I plot rotated y, one is just a rotation of the other. So I don't know if you guys can see, but you'll see that we're just going to rotate. So you pay attention to some of the, I guess, weird features of this thing, and you'll see that it's just a rotation. One is just a rotation of the other. Okay, and then if I take EV1, what it will do is we'll just collapse. So here's our original data in 2 dimensions, and there's high correlation between x1 or y1 and y2. Okay, and so we found the eigenvectors, and if I multiply our data by our eigenvectors, it just rotates it. So you'll notice these 2 dots out here just end up, right there. So this is just a rotation. Okay, but our data still exists in 2 dimensions, and so when I reduce it down to 1 dimension, basically everything is just going to collapse down to one thing. So these 2 dots that are basically, they're different, but when I collapse them down to 1 dimension, they'll basically show up as the same point along here. Okay, so you'll see these 2 dots just kind of close up here. All of these dots will kind of just fall on top of each other, but you'll still kind of see these ones out there as well. So that's what it means to reduce reduce your data. Okay, so if I do a plot of basically just to dimension 1 will be y-centered times our first eigenvector. I can plot EV1 and repeat 0 100 times. Oh, sorry, not sorry, dim1. So I don't know if we can tell this. So this is just so. So here we're going from 2D and then we're just reducing it down to 1D. Okay, can we see that? So original data, we rotate it and then we collapse it down to 1 dimension. Okay, and that's basically what principal components analysis is you're finding the rotation of the data, and then you say, well, now that we've got it here, I can basically throw away some of the information. Okay, and we're not losing too much. It's a little bit I don't know. Did you guys take the SAT? Maybe, maybe not. Okay. So there's 2 components or 3? There's just 2, right? There's it's basically a verbal and a math part. Okay, and so you can go from 200 to 800 on any of these individual things. So, but if you have math and verbal, you can have and then you have total. Basically, the total is a linear combination of math and verbal, and the linear combination is just 1 times math plus 1 times verbal. Okay, but you could do anything else. You could do something like that, and so when you do math and verbal, you can somebody who has a 750 math, 750 verbal will be 1500 total. You can also have 700, 800, and 800, 700, right? So these would all be very good scores, okay? But these are different, but they all would show up exactly the same if you do this. So if you use only the total score, you lose some of the subtle differences between these individuals. And that's basically what happens when you do dimension reduction. We're saying, you know what? These 3 individuals, we can treat them the same, is basically what we're saying, okay? When you reduce it down to this, okay? Because in to kind of capture this, you have this, right? If you say the total is 1 times math plus 1 times verbal, okay, you can capture the exact same information by doing 1 math minus 1 verbal, okay? And then so this would be, I guess, a difference, and you would have a 0, and you would have a negative 100, and a plus 100, okay? And if I presented this information to you, and I presented this information to you, these 2 things contain the exact same information. Okay, this is the original data, looking like this. Okay, and this would be the rotated data. Okay, this is because here you have. So you basically have this and this. And then over here, after rotation, you're going to have 1500 and then plus 100 and minus 100. So this, and then if you had someone else, I don't know, 500, 500, 500, 450, this would be total 950 and a difference of 50, and so that person would be, down here or something like that, which would be, also 500, 450, probably be somewhere over there or whatever. But basically, you have some kind of linear combination here. These are orthogonal vectors, and this would just be a projection of the original data to this other space, a rotation of the data, kind of like this. Contains, by keeping both variables, you can capture all of the exact same information, just kind of rotated in a different space. And then, and basically you're saying, well, this is, just the x variable is the most important one, and so I can throw away some of the information there. Okay, and that's principal components analysis, kind of in its basic form. And I guess next week, I'll talk a little bit more about principal components analysis, kind of just like maybe a fun little demo, and then I guess the last couple lectures, I'll talk about the final exam, and then the last couple lectures will just, I guess, be like interesting things and fun things that I won't test you on. So we'll wrap it up there. Okay, have a great weekend. We'll see you week 10 when we come back. Oh, I have to give you, how many view quiz answers did I give you? One. Just one? Oh man, okay, all right. The other two answers are C and B. C as in cat, B as in bear. Okay, we'll end there.